The artificial intelligence industry is a heavy industrial operation born from a specific hardware bottleneck in 1990s consumer electronics. The digital infrastructure of the cloud is composed of physical matter, crystallized silicon, copper piping, and megawatt power grids. In the late 1990s, the technology sector was focused on the constraints of personal computing and the first generation of consumer 3D graphics. The standard central processing unit, the CPU, was a generalist. It solved complex tasks one at a time. When forced to calculate the repetitive geometry required for 3D video games, these processors reached a hard architectural limit. In 1999, Nvidia released the GeForce 256. This chip offloaded the transform and lighting mathematics from the CPU onto a dedicated parallel hardware architecture. This pivot to faster video game rendering established the high-speed computational framework that would later sustain large-scale neural networks. This CPU architecture dedicates massive space to the control unit for single-thread tasks. It's like a senior professor solving one difficult problem. The GPU uses the opposite philosophy, maximizing arithmetic logic units. It's 10,000 students processing an entire matrix of calculations simultaneously. Rendering a 3D pixel requires billions of simple matrix multiplications. Training a neural network requires this same mathematical process. Until 2006, this immense parallel processing power was restricted. The chips only understood languages designed for graphics rendering. Nvidia engineers then developed CUDA, a compute architecture that allowed general programmers to send non-graphics data directly to the GPU's dense ALU grid. This integration made neural network matrix multiplication computationally feasible on consumer hardware. This computing server presented by Nvidia CEO Jensen Huang shows the scale of this evolution. The gaming hardware of the 90s has transformed into massive server racks designed for enterprise-level parallel computation. Because AI research was built on top of the CUDA layer, the industry is structurally linked to this specific silicon architecture. Scaling AI requires adding more ALUs to a single chip. This forces transistors down to the nanometer scale. Transistors at this scale cannot be printed with conventional light because the wavelengths are too thick. This created a hard physical limit for the hardware. This building in the Netherlands is the headquarters of ASML. They manufacture the only machines capable of extreme ultraviolet lithography. Producing a modern AI chip requires light with a wavelength of 13.5 nanometers. This state of plasma does not occur naturally on Earth. Inside the machine, a molten tin droplet falls through a vacuum. A laser strikes it, vaporizing it into plasma that emits the required ultraviolet frequency. To sustain this light, the internal laser hits microscopic tin droplets 50,000 times every second. In foundries like this, personnel work in strictly monitored clean rooms. At the nanometer scale, a single particle of dust ruins the entire parallel architecture. Each lithography machine costs over $200 million and requires multiple cargo planes for transport. The scaling of AI is constrained by the manufacturing output of this one mechanical engineering company. Moving from the microscopic scale of the silicon to macroscopic infrastructure reveals a new constraint. Computational scaling is reaching the energy wall, where growth is limited by the capacity of the electrical grid. A single major AI training run can require the same power draw as a small city. This data center floor shows where artificial intelligence resides. It is an industrial environment composed of server racks running at capacity. This computation generates massive heat. Managing it requires miles of liquid-cooled infrastructure and copper heat sinks to protect the silicon. This heat production has increased global demand for high-voltage transformers, liquid cooling systems, and copper cabling. Standard consumer interaction with AI occurs through a digital interface on a mobile device. The intelligence generated by these models depends on the high-voltage transformers and industrial foundries of the global power grid.